a pleasure to introduce our first speaker of the afternoon. It's Bruno Premoselli, and he's speaking on non-compactness of initial data sets in high dimensions.
Okay, so good afternoon everyone. Welcome back to this afternoon session. So of course, before I start, let me thank the organizers of this conference for inviting me here today, giving me the opportunity to talk about my research work. Okay, so today I want to show you a result about the non-compactness of initial data sets in general relativity in a high dimension. High dimensions for me will mean larger than 6, which is large enough for many geometers already. And so initial data sets will be initial data sets for the evolution problem of the Einstein equations. Okay, so just maybe to settle the problem, let me start by recalling you very easy things, which I'm sure most of you know very well, but will be useless. Well, they won't come into play in the talk, but they will help me settle the problem and explain what I'm talking about, right? And after this, I will investigate some kind of conformal PDE problem related to this. Okay, right. So let me start by recalling very basic facts about general relativity. Well, as you all know, the geometric setting of general relativity is the one of Lorentzian geometry. So here, for me, M will be a Lorentzian manifold of dimension n+1 and bigger than 3, right? And I will work in a scalar field theory. So in a scalar field theory, you endow your manifold with a scalar field, which is just a smooth function on the manifold, plus a potential, which is just a smooth function in R, right? And in this theorem, asking for your geometric objects to be a space-time, so model the physically realistic situation, amounts to solving the Einstein equations, which with a slightly changed form to take into account this scalar field. So here on this left-hand side, you have the usual form of the Einstein equations, and on the right-hand side, you have the specific form of the stress energy tensor in the scalar field theory, right? This is just a geometrical equation which accounts for local conservation of energy. Okay, so this model can be, this scalar field setting can be used to model relevant physical cases, like the vacuum case, for instance. You take everything to be 0, psi and v, the vacuum case with a positive cosmological constant. You take your potential v here to be a positive constant, and also if you play with quadratic potentials, you will end up having massive Klein-Gordon fields, right? So this is just the setting. Usually, for causal reasons, we work with global hyperbolic spacetimes. Okay, I will not recall what they are. They are spacetimes enjoying nice causal properties. For me, they will just be product spacetimes. Oh, sorry. So my product spacetime will be a Riemannian manifold, so Riemannian for the induced metric, times R. So here R plays the role somehow of a temporal derivative, of a temporal coordinate, and this setting will allow us to express the Einstein equations as an evolution problem. Okay, but as you know, the shape of the Ricci operator is not hyperbolic, so even the notion of initial data set is not so clear from now on. So that's what I will try to define exactly right now. So just to fix the notations, everything restricted to M will be denoted with a tilde, right? So we'll call J tilde this Riemannian metric restricted to M. Nabla tilde will be its Levi-Civita connection. There's another geometric component which comes into play. It's K tilde, which is the second fundamental form, of the embedding of M into M times R, of course, for the Lorentzian metric here, right? And then there's psi tilde and P tilde, which are the restriction of the scalar field and of its temporal derivative, temporal meaning with respect to the Lorentzian normal, future directed to M, right? So there's a huge result in the field, which was proven in the 50s by Yvonne Choquet-Bruat and later on improved by Yvonne Choquet-Bruat and Jarok, which is the result that opened the field of mathematical general relativity that is known today, and it establishes kind of a well-posedness for the Einstein equation. So this result exactly tells us that if you want to look for a space-time which is a product space-time with a Lorentzian metric and a scalar field, so if you want to have something like this which solves the Einstein equations, then this is equivalent to the fact that all these quantities defined in restriction to M satisfy some other system of equations, right? This other system of equation is called the constraint system. Of course, there's an S missing here. The constraint system, because it constrains the admissible initial data for the evolution, and it's written down here, right? So it's made of n+1 equations. The first one is a scalar equation. The second one is a vector equation or a one-form equation. And it's highly underdetermined. You have n+1 equations for a quadratic number of unknowns. Okay, you have a metric which is a known, a second fundamental form, so it's a symmetric tensor, plus you have two functions, right? So even in dimension 3, it's underdetermined. And this theorem is really an equivalence, right? If you start with 4 objects, a metric, bilinear form and two functions which solve this abstract system on a manifold M, then you know they will generate some spacetime, some globally hyperbolic spacetime. So the picture is really the following one. You start with a manifold M, these objects here, and from this you get some globally hyperbolic spacetime. It's constructed with the Zorn's lemma. I'm not going into the details of this fact, but...
Does it really exist on the whole of Mn cross R? Can it not develop singularities after?
Well, that's the fact, actually. R here is kind of a global temporal derivative, and it's not the proper time of geodesics, for instance. So if you want...
You're cheating.
Yeah, this...
There's a root normalization behind it.
Yeah, exactly. So this R coordinate here is kind of the coordinate of a foliation by space-time hypersurfaces, which is in your system. If you start in Minkowski with just...
The metric might not be complete on Mn cross R.
No, it might not be complete. It might have singularities and so on. You know, if you start with the Minkowski segment, you will have, you know, your R coordinate will measure in which of these sets you are. So, of course, the proper time of geodesics here is just the length of the length of the causal segment, right? So it's got no clear physical meaning, but at least that's the idea. Okay, so this is the reason why, this is the reason for the importance of the constraint system, because this system, gives you admissible initial data sets from which spacetimes evolve. So of course, the problem of understanding, for instance, the property of spacetimes is not reduced to just finding solutions of this system, but still, it's interesting to look for solutions of this system because they produce initial data sets. Okay, so that's what I will try to do. So this is just to settle down the problem. We will not really see this system later on. We will see a reformulation of this system, which is the one which is written here. I will explain how later on, but this is just to get the idea. Okay, so this is a very nonlinear system, right? There's intrinsic geometric quantities for the manifold. So this R stands for the scalar curvature. There's extrinsic geometric quantities, like the trace of the second fundamental form. There's physics quantities here, right? So it's not so easy to solve, and I will show you right now a method which was initiated by Lichner-Ovitz in the 40s and later improved by Choquet-Bruyas in New York. So it's a very simple idea from the physical point of view. You have an underdetermined system, you make it determined, right? So, well, if you have n+1 equation, you look for solutions under a specific class, a specific form, which depend on n+1 parameters, so as to have a determined system, right? So, what will be the class of solutions we will look for? Well, it's got this form here, and the idea is that you, among all the unknowns you have, you arbitrarily choose a subset of them, to which you give fixed values. You consider these unknowns from now on as given physics data, okay? And then you solve for the remaining unknown of the problem. Okay, so for us, the physics data will be two functions psi and pi, which will account for a scalar field data, a potential v, this function from R to R, a function tau, which will play the role of a mean curvature, and a symmetric and divergent, traceless and divergent free bilinear form, the TT tensor that Bern mentioned this morning. This bilinear form here somehow plays the role of a gauge choice. So, okay? And so the method is called the conformal method, so there ought to be conformal geometry in it, and it's in the choice of the metric, right? So the solutions of my system will be looked for under the specific form here. The unknown metric J tilde will be looked for in the conformal class of a reference metric G. So here G is given, right? And J tilde is just some unknown conformal factor U times G. The power here is a suitable power that often appears in conformal geometry to get nice conformal change in your operators, right? And well, my scalar field data will just be psi and pi up to something which depends on U again, and my unknown second fundamental form will be, well, a tensor with a trace part, traceless part. The trace part will totally be given by this function tau here, which is the mean curvature with respect to the intrinsic metric, to the new metric, sorry. So tau will indeed play the role of a mean curvature if we manage to solve the equations. And the traceless part of my tensor will be totally given by U. Of course, there is again this conformal factor, plus some first order derivative of some unknown vector field or one form, right? And this first order derivative is of course a geometric derivative, and it's exactly the conformal killing operator, which is written here in coordinates, and which is just the traceless part of the usual killing operator, right? So it's not surprising to have this conformal operator arise here since we are in the conformal setting, okay? So about the choice of this specific form of solutions, it's not so clear why Lichnerowitz and then Choquet-Bruat considered this form here. For the conformal metric, it is somehow, because in the previous equation there was a scalar curvature term, and it's been known for a long time that scalar curvature behaves very well with respect to conformal changes, right? The choice of this splitting here for bilinear form comes from the fact, well, that's maybe one reason, that what you get in the end is elliptic, right? So that's probably a suitable choice. So now you take this explicit expression here for the unknowns you're looking for, you plug it in the previous constraint equation, and when you work out all the computations, you find out that this parameterization here solves the constraint equation. So you get initial data set here, if and only if your two unknown u and w, which are the new parameters of the problem, solve a new system of equations, which is the system which is written down here, okay, and here also. It's the same one. So this new system is called the Einstein-Lichnerowitz constraint system, right? And now we're happy, because now we have a determined problem. We have still n+1 equations. The first one is a scalar equation, the second one is a vector one, but now we have n+1 unknowns. Right? Our unknown are u, a positive function, conformal factor, and w, a vector field. Okay? So just to make things clear in this system here, you have like...
So do you assume that tau is constant? Because usually there's also the tau term.
Yeah, sorry. My x here is nabla tau.
Ah.
So that's... I wrote it actually in the... I will explain it later. So I wrote it in the general form. You see all the coefficients actually, h, f, x, and so on. They depend on all the physics data I chose before. So they depend explicitly on them. So for instance, my x here is nabla tau. I just wrote it here because otherwise expression gets too wide, but I will explain about this later. Okay? So no, tau is not constant here. It's very general. There's no problem. And this system here, you have two differential operators. So a Laplacian on functions, which is just the usual Laplace-Beltrami Laplacian. So it's a non-negative Laplacian. And you have this vector Laplacian here, which is a Lamé operator. So it's the same operator which arises in mathematical mathematical elasticity, sorry, and which is defined as minus the divergence of this conformal killing derivative. So it's also a non-negative operator, whose kernel are the conformal killing fields. Okay, so you see the same operator arises here also. And well, you have a nonlinear system, right? You have nonlinearities a little bit everywhere. So in particular, you have this nonlinearity here. So if you have u to the power 2 star minus 1, and 2 star is a shorthand just to denote the power 2n over n minus 2. So here, I wrote it with the explicit powers. This power 2 star minus 1 will be the prominent nonlinearity in what I will say, because it will be responsible for the phenomena that I will investigate. Okay, but keep in mind that you have a strong coupling to this vector field x here, and you have a nonlinearity here again, so you have a nonlinear system, right? So solutions of this system are known to exist, right? So this parameterization proved useful to construct solutions of the initial constraint equation, right? There's results that say that provided your physics data are mild enough, you can construct solution. But that's not what I will say today, okay? Just, I'm telling this to you so that you know that I'm not only like playing with things that don't exist. But today I will not be interested in existence issues for this system, but rather in blow-up properties for this system, okay? So what do I mean by blow-up properties, and why would I like to investigate them? Okay, well, before going into the details, because there's still a little bit of suspense here, let me be clear about what I will consider, so very clear about the setting of my problem. So from now on, this space manifold, so what originally was a space manifold and on which I'm writing down this system, for me will be compact without boundary. Okay, so that's a technical assumption. And the assumptions of my system here, they will be always assumed to satisfy some conditions. I will assume that the linear operators which I have are coercive. So this operator here, Laplacian plus h, is coercive, means positive with no kernel. I will assume that my geometric Laplacian here, vector Laplacian, has no kernel. So this is a generic assumption. And most important, I will assume that this function f here, which appears in front of the nasty nonlinearity, you still don't know why it's nasty, but it is, I will assume it's positive, right? And so now let me give you the explicit expression of the coefficients in terms of the physics data of the problem. So you know that I told you this vector field x is up to some constant and some sign, the gradient of the mean curvature. This vector field y here, just a constant one, it's not a constant one-way. It's a constant term in terms of u, and like you see the components of the scalar field and so on. Okay, so in particular, this assumption that f be positive is found when you have non-trivial non-gravitational data. Okay, if you are in the vacuum case, this function v here would be 0, so you would have a non-positive f. Right? So this case here, which is usually referred to as the focusing case, by analogy with the case of Schrödinger equation, arises when you have general non-gravitational data. Okay, right. So now that the setting of the problem is clear, let me tell you what I will investigate more precisely and why I'm interested in blow-up phenomena for this system. Okay? The fact is that my system is nonlinear, and I told you that this nonlinearity here plays a prominent role. Why so? Well, the fact is that this is a critical nonlinearity, critical in some sense, and in terms of gain of regularity into energy spaces. Right? To be more precise, usually when one encounters elliptic system, one is very happy because whenever you have a Laplacian, you automatically gain 2 degrees of regularity. But the fact is that when you have nonlinear equations, this gain of regularity is compensated by the fact that you have a nonlinearity. Okay? So if you started just with the scalar equation, look at the scalar equation, you would like to assume that U lies in some reasonable energy space, Sobolev space, for instance, without going too much into the details. Well, you belong to some LP space, you would like to regularize twice to gain more regularity, and to say that then you get a smooth solution with uniform a priori bounds on every derivative, right? The fact is that this nonlinearity here is exactly the threshold from which you do not gain additional regularity. Okay, so what happens is that if you just start with an energy bound on your functions here, you do not get higher regularity bounds. You do not get C1, C2, or smooth bounds. Okay? And this nonlinearity here, for this reason, makes what I call blow-up phenomena likely to occur. So what are blow-up phenomena? Well, the model case of blow-up phenomena are these family of functions here, which I call standard bubbles. Okay, so these are a family of functions in Rn, which all depend on n+1 parameters. So they depend on one scaling parameter lambda, it's kind of the 8 of the bubble, and one center parameter x0. And if you draw them in Rn, they really look like this. Okay, it's like it's a decreasing profile, which here decreases like 1 over the distance, the power n-2, and the value at the center x0 is 1 over lambda at the power n-2 over 2. Okay, so in particular, when you make the value of your scaling parameter lambda vary, you have functions which become larger and larger at the origin. Right? Your family of functions looks like this. So you have functions which blow up, which become bigger and bigger in pointwise spaces. This is true also for the first derivative. Okay? But the point is that all these functions satisfy the same critical equation, so their Laplacian is equal to themselves at the power 2 psi minus 1, so exactly the same power which is here, and this equation is in some sense a simplified toy model of this system here, and the fact is that they all carry the same quantum of energy. Okay, so all these functions have the same fixed positive energy, it's a universal constant which only depends on the dimension, but they blow up. Okay, so this is the phenomena of you do not gain automatically regularity, because even if you start with functions which all have the same energy, you have this kind of concentration phenomena that occurs, right? And this is not only related to the fact that you are on Rn, that you have symmetries, or that you choose specific functions. Actually, whenever you work on a manifold and with equations or systems which are variations around this toy model here, you see the same kind of phenomenon. So it has been constructed by several authors, Drouet et Beff, all the first ones, Esposito, Pistoia, Vetois, Robert Vetois, Pistoia, Vaira, Vetois, and Tizi in the last years, that generically speaking, when you have a critical power like this, under some conditions, of course, well, you can expect, you need to expect this blow-up behavior here, okay? And this behavior, another way to see it, is to say that, well, when your equation shows a blow-up phenomenon like this one, is that it's because you do not have uniform a priori bounds for solution. Okay, so you can see this, the existence of this blow-up phenomena as a failure of your equation to provide you uniform bounds for your solutions, which are uniform also in the choice of the coefficients, okay, which are uniform in everything. So one question that arises naturally here is, well, I have my system here, which is actually much more complicated in structure than this model equation, because there's a coupling, there's another nonlinearity here. So I might wonder whether this blow-up phenomena still hold, if I will see them also for this system here, okay? And this is, well...
You said that there's the wrong sign, so if f were -1,
there would be no blow-up
there
phenomenon.
would be no blow-up
No.
phenomenon. So you can't write down these bubble equations if there's a minus sign
No.
next to that B.
If you put a minus sign here, every solution is bounded in Rn, and
You
it's
can write down the a priori bounds. So
yeah. You can. Well, it's just the maximum principle actually. If you put a minus here,
yeah, of course.
so it's very easy. So yeah, the fact is that these law phenomena, and thanks for pointing this out, really occur because you're in the situation where the sign here is like the positive and somehow bad sign.
And the critical nature of it is because that's the power at which you can't use Sobolev multiplication anymore.
Exactly. So the criticality is also that when you usually start with your Sobolev space H1, so the space of functions which are in L2 and whose derivative is in L2, it embeds in all the backspaces. It embeds compactly in all the backspaces below 2 star. Okay, so the embedding in 2L to the power 2 star is not compact, and this is a counterexample of compactness actually. So it's not compact because of this family of functions here.
And it's more like examples they actually describe spheres. This may be also important.
Sorry?
This bubble they describe spheres.
Yeah, exactly.
That we have to take to get a sphere.
Exactly. So this bubble here is exactly the what makes the conformal group of the sphere non-compact. This is just up to some slight modification. This is just what you get when you have with the stereographic projection. You can use you can change conformal idiometric on the sphere, and the family of conformal changes you get is this one when you change the distance here by the intrinsic distance on the sphere. But that's everything is rated to this, right? So that's a fact. So one might wonder why, if blow-up phenomena appear in this equation also, and it's of interest to analysts, of course, but it kind of makes sense here in view of the reason why we introduced this system, right? Because, well, just a reformulation of what I'm saying is that if you have a blow-up phenomena in the spirit of these bubbles here concentrating, well, automatically you know that the set of solutions of this system here is non-compact in some strong topology, for instance, the C2 topology or even the C01, right? So this is already a structural information on the set of your solutions. You know that you will have families of solutions which become bigger and bigger, okay? So since you have a non-compact sequence, this automatically tells you that you have an infinite number of solutions first. So you have an infinite number of blowing up solutions, right? But here, in the end, well, you introduced this model here to generate initial data sets. So here you're creating an infinite number of them, which might be good, even though you don't really get a preferred solution here. They are blowing up, so you don't really know what's going on. And most important, with these functions here, with the solutions of this system, you are creating initial data sets, right? This was the parameterization that we had before. So in particular, if you have functions uk and vector fields wk which blow up, well, the geometric objects that you will construct will develop like singularities. So you will have a metric whose injectivity radius goes to 0. It amounts just to like somehow gluing a sphere at a point on your manifold. And you will have a second fundamental form whose pointwise norm is not bounded. Okay, so this, it's not clear that from the evolution, that for the evolution problem here, this will really cause problem, right? You cannot say that when you start with this kind of data, you will get a singularity in finite time. You cannot say this, but still, it's not really satisfactory because, well, you don't really know what you're constructing. Like you're getting somehow pathological data and so on. And so another way to say it, just what I told you before, a reformulation of it, is that if you have a blow-up phenomena of this, since all the coefficients of your system depend on the physics data which are in the background of the model, there's a problem because, well, you have a system here which takes some physics data and which produces solutions which are not really uniform on the choice of the physics data of the problem, right? And they're not even uniform up to small perturbations of the physics data. So this is something that you wouldn't expect. You would expect that, I don't know, maybe some error in the choice, in the measurement of your mean curvature would not create solutions standing dramatically far away from what you expect, right? So, in other words, investigating this property of blow up is also a way to understand, well, to which point you can push your conformal method, right? If the solutions which are created by the conformal method are pathological and are blowing up, well, maybe it's because you don't need them, right? Maybe you should do something else to construct initial data sets. Okay, so this is what I would like to investigate today. And so there is something which is known about this blow-up phenomenon, and actually it's the other way around, right? So actually the first question that was investigated for its system for this reason, to understand somehow the relevance of this modelization here of the conformal method, was the question of compactness. So it's exactly the dual question of not blowing up. So you take this system here, you look at the set of all its solutions. Actually, this system has generically at least 2 solutions, so there is not only one. So it makes sense to look at the whole set, and you ask whether the set is compact or not, which is exactly the same thing as saying that you do not have this kind of blow-up behavior. Okay? So this question was investigated by Olivier Druet and myself, first in dimension 3, and then in any dimension. So we did it on a locally conformally flat manifold. This is a technical assumption, but it does not come into play into the behavior, and also it will disappear later on in the talk. And we found that actually there is no blow-up for the system here, so there is no nasty solution as this one here, under some conditions. So first of all, in small dimensions. So this is surprising, but you have a dimensional hiatus. Hiatus. You have a dimensional hiatus, which tells you that in small dimensions, so for me it's 3, 4, and 5, you have no blow-up. So the solutions which are produced by your system always live in a compact set in C2. They're even actually generically isolated, and they're generically stable. So this is very satisfactory. And in higher dimension, if n is bigger than 6, then you start to see compatibility conditions that come into play. Okay, so if n is bigger than 6, well, then you have to assume something. You have to assume that the coefficients of your system, that is your physics data, behave well one with respect to the other. So there is some compatibility between the physics and geometric conditions of the problem. So you see here, well, for instance, your coupling vector field need not have a 0. Right? If it's got no zeros, then your system is stable. Of course, this is also a topological assumption on the manifold, so it's kind of restrictive, right? If your vector field acts as a 0, you can go to second order, and you have this kind of condition here. And this condition here expresses some balance between the coefficients of your equation, h and f, and the geometry of the problem. So here, I change the notation, but Sg is the scalar curvature of the Riemannian metric. Okay, so that's a second order condition. The good thing is that in dimension 3, at least, which is the physical dimension, this system produces nice solution. Okay, so what is left to understand to fully grasp the blow-up behavior of this system is what happens in I dimensions. So this is true for every dimension, but the question is this sharp? Like, can I say that as soon as this condition is not satisfied, I will have blow-up solutions? Okay? And the answer actually is yes. Okay? And this is the main and only result that I will discuss today. It's basically a result that tells you that whenever you are working in I dimension, non-compactness phenomena are natural and appear as soon as the stability condition is not satisfied. Okay, so in more tangible terms, we work on a closed Riemannian manifold of dimension bigger than 6, of course, such that this geometric operator has no kernel. So this is a technical assumption, and there is no conformally flatness assumption anymore. What I'm telling you is that I can find coefficients, so hf, pi, sigma, x, and y. So I can find a choice of these coefficients, which are regular. Okay, so I'm not cheating by taking low regularity data, which are in the focusing case. So focusing case means that this operator is positive, this has no kernel, and most important, that f is positive here. I insist on the fact that I am taking a fully coupled system, so my coupling vector field x here is really non-zero, so it's not a constant which simplifies the problem or not. And so for this choice here, I can find the blowing up sequence of solutions of my problem, okay, which blow up somehow like this. The scalar function u blows up like this, so it's got concentration points, it's got a fixed energy, and it's got a limiting profile. And well, the vector field doesn't really blow up like this. The situation is a little bit more complicated. The blow up of the vector field is more global. Okay, it's given, of course, by the second equation. So you can see the second equation as kind of taking the average of this blow up here of the whole manifold, which still blows up. So in particular, the coefficients which I have here, of course, they do not satisfy the assumptions of the previous stability theorem. Okay, so in particular, well, the inequality was the other way around on the previous slide. So here, my coefficients have to satisfy this large inequality somewhere. And of course, the concentration point will be the point where they exactly satisfy this. Okay. So with respect to what I told you before, this automatically tells us that this system has an infinite number of solutions under this assumption. Okay. So let me insist on the fact that this is a constructive result. Okay? I'm not exactly telling you that whenever I take functions which satisfy this, I have a blow-up phenomenon. Okay? I'm taking you that up to a perturbation this is true. Okay? So if I take functions that satisfy this, I can slightly perturb them to have blowing up solution. But it's not true, of course, for every choice of data like this. But at least I can always find data which satisfy this and for which we have a blowing up sequence of solutions. Right? So let's say that in I dimension, my system here can be trusted, is reliable, only as long as the opposite inequality holds. Right? Okay, so in the last 15-20 minutes that I have, I will try to give you a sketch of the proof of this result. Okay, so now,
so you get a countable number of blowing up solutions, or you can get a family of.
So you get a countable number. Yeah. With this method, you get a countable number, and I don't think you can get a family because, well, I wouldn't be so sure about this, but generally speaking, with this kind of equation, the criticality is not a problem here. Your solution will generically be isolated. Okay, so because their linearization will be invertible, not stable, but invertible. So it's very unlikely to find a continuous path of blowing up solutions. It's not a parabolic problem, it's just an elliptic one, so you get a discrete number of solutions which blow up. Okay. And of course you can choose their blowing up point, you can choose somehow the way they blow up. Okay. So this is a constructive result, right? We will choose suitable coefficients, we will construct solutions. And how will we construct them? Well, basically it's gonna be some kind of gluing construction, okay, a gluing approach. So we have this system here, the same one that we have had since the beginning of the talk. And we want to construct a blowing up solution. So we expect there is this critical power, and our bet is that this critical power will be dominant with respect. So let me just look at the scalar equation. My bet is that this critical power here will be dominant with respect to this other term, which is kind of scary because it's a negative nonlinearity, it's a quadratic coupled term. But still we expect that what will give us the blow-up phenomena will be this term here, right? And we know, we come back to the model equation, we know that we have a family of blowing up solutions, these standard bubbles. So somehow we expect that at least in the region where my solution becomes bigger and bigger, well, the behavior will be given by this family of solutions. Okay? So my bet here is the following one. I will take a solution which looks like a standard bubble, so put on my manifold, so there is a slight modification just to take account of the fact that you have a geodesic distance, but it's very simple. A standard bubble plus a weak limit. So this weak limit here is just one given solution of the system, it exists, plus some remainder.
When you call it the weak limit, you mean that if you took the limit and threw away the bubbles, you'd get the weak limit?
Yeah, exactly. So it's really a weak limit in the energy space H1. So, of course, so my bubble, they do not converge strongly in H1 because they all have the same energy which is fixed, but they converge weakly in H1 to 0. That's another phenomenon of non-compactness. It again amounts to having embeddings which are not compact. That's exactly the same phenomenon. Okay. So my bet is that I will be able to find, so my bet is that first, this weak limit plus the bubble is almost a solution of this system. So it's an approximate solution. And I hope to be able to deform it by adding some other function, which will be small compared to what comes first. And I will be able to deform this into a proper solution of the system. Okay. At this moment, I don't really know how this term here will behave, but I hope that I will be able to do so. Okay. And of course, the smallness of this term here will have to be chosen kind of carefully, right? This idea of gluing, of deforming something into a proper solution is very standard, very easy, but it comes always to choosing the right approximation and the right deformation. Okay? But there is a problem, which is due to the coupling of the system. So if I were working only with the first equation, only with the scalar equation, performing this would be very simple, because in the last 15 to 20 years, there has been lots of work devoted, lots of constructive machinery to develop gluing methods of this kind. So these kind of techniques are usually called Lyapunov-Schmidt methods or finite dimensional reduction methods. And they work pretty well with even critical, that's not a problem, but they work pretty well with variational nonlinear equations, right? So if I were to work only with the first equation, I would have a variational one, and this would be very easy. The problem here is that I have a coupling. And to be more precise, the problem lies here, in this power here in the coupling term. Okay? Because I want to work with a fully coupled system. So I want my x here to be non-zero. In other words, I'm thinking about the case where my mean curvature is not constant, right? And because of this term here, my system is ill-posed in a variational way. Why so? Because if I look at the first equation, I would like to work with a function u which lies in some energy space, for instance, the Sobolev space H1. Then I have embeddings, so I know that u belongs to L to the power 2 star, okay? But this means that my right-hand side here is merely bounded in L1, okay? And when you have a solution whose Laplacian lies in L1, actually you don't get anything. Right? So in this second equation here, I get, the second equation here is not even well posed from a variational point of view, right? So if I only work with energy spaces, so trying to apply this machinery which exists and which are pretty effective, it doesn't give me anything, right? So it doesn't work because actually this power here is super critical in some sense with respect to the scalings and to the energy method. Okay? So I will have to perform my gluing in another way, and I will just perform my gluing in a continuous way, right? These blow-up phenomena here are really pointwise in essence because you have a pointwise explosion, you have a pointwise well, for derivatives also. And so you see there is something more than mere energy blow-up. You cannot think about these things only by energy consideration. Okay, so the right space in which you work are strong pointwise spaces. Okay? So how we will proceed? Well, we will kind of put many different techniques together. So we will perform a constructive method working in pointwise spaces together with kind of a fixed point method. So what is kind of ping pong method? This is the topological method, a fixed point approach, often used when you have systems. So basically you start by solving the first equation, you plug it in the other one, and you play around until you get something. Okay? So we will look for a solution which looks like a standard bubble, what we expect to be the blow-up behavior, plus a weak limit, plus a remainder. Right? And my remainder will be chosen to be small in a uniform pointwise sense. So I will look for this remainder here into the set of solutions which globally on the whole manifold and pointwise are bounded by a constant which goes to 0, which I call epsilon k, times the ansatz of my solution, so times my approximate solution, which I showed before. Right? And here, if you have seen it, I'm adding some parameters. So I'm saying that my function here, my solution, will depend upon n+1 parameters, which are a scaling parameter and the center parameter, which are of course reminiscent of the n+1 parameters which I had for my bubbles here. So an 8-1, a height one, and the center parameter. Okay. And the purpose of the method, if I want to find a discrete set of solutions, will be for each value of my sequence parameter k, I want to find the value of the parameters, lambda k, sigma k, and a remainder here, for which this expression here is indeed a solution.
To this answer, shouldn't you add a power of f in front of the b lambda psi k?
Yeah, actually, my b lambda ck is not the standard bubble as I gave it before, but it's got an f inside of it. So my b lambda ck would be it takes into account the fact that so here the model equation which you're expecting is something more like so Laplacian u equals f times u to the power 2 star minus 1. This is what you expect to find, and actually you even put f at some given point which you expect to be the concentration 1. So here the solution, there's just a simple scaling, and the standard bubble is something like so lambda over lambda square plus, and then there is f on x0 over n times n minus 2 times the distance square. Okay, put everything at the good power. So of course the f, maybe you don't see it, but the f term arises here in front of the. Of course, there is an f term. This is you have to take it into account, but that's just not really important here. Okay, so this is what we will try to do. We will try to use this pointwise construction to find a solution for a system. So more explicitly, how does this work? The proof goes through like 3 big steps. It's a ping-pong method plus some application of the integral machinery, which I would have liked to use, plus some a priori asymptotic analysis. Okay? So there is a 0th step, which is just the beginning of the ping-pong method. So I expect my remainder to live in the space of functions which are uniformly bounded by some constant times my approximate solution. So you start with a function which lives in this space here, right? And for a ping-pong method, the first thing I do is I take my u here to be, you see, the bubble plus the weak limit plus phi, and I solve the vector equation for this. Okay? I can always do this because I assume that my vector Laplacian here has no kernel. Right? This provides me with a vector field wk, which blows up. Okay? What is comfortable here is that since I have pointwise bounds on my phi, I get, with Green's formula, for instance, I get pointwise estimates on my wk. Okay? And I realize that it also blows up, but still, at least, I know how it blows up. Okay? So then, I want to run my ping-pong method. So I take my wk here, I plug it in the scalar equation, and so I plug it here, and I see it as a coefficient. Okay? And now what I would like to do is to solve this scalar equation here, okay, for a new blowing up solution, and then make some fixed point procedure. Okay? So now I'm really happy about it, because I told you if I were to work with only an equation, it would be simple. So now I'm just working with this equation. So now there is a whole machinery that has been developed in the last 15, 20 years, and I can apply it. So of course you need to check that the applicability works here, but it's what you do. So you can construct a solution of this equation which blows up and which looks like a bubble plus the weak limit plus some other remainder psi. Okay? And since this family of methods here are energy methods, my new remainder psi only lives in H1 a priori. Okay? Because I'm working in H1 space is just a variational construction. The point is that here I don't really have the equation I would like to have. Okay. I have some additional red terms here. Why so? Well, the fact is that I cannot just apply some inverse function theorem as you usually do in gluing methods, because actually my equation here, when I apply it to the approximate solution u0 plus the bubble, it's got a kernel. Right? And the kernel elements are these elements here which you find here. So actually the only thing you can do is to apply an inverse function theorem in the orthogonal of the kernel. And then you can solve the solution. But so in the end, you don't really solve your equation. You solve your equation up to some kernel elements. So these z, gk here are the generators of the kernel of the linearization of the equation. And in front of them, there's a family of coefficients. Okay? So if I were to make these coefficients vanish here, this would be great. Okay? But these coefficients depend on my parameters. So I still have hope to play with them. Okay? And so this is just a refinement of the usual inverse function theorem. Okay, so, but the problem is that the remainder which I get here only lives in an energy space. Okay? And now comes the hard part of the analysis of the method, and the fact is that you started with from a remainder phi, which was pointwise bounded by this, because that's what you expected, right? You somehow felt this would be the good choice. And in the first two steps, we just ran a ping-pong method. We applied the machinery, which was very useful, but it gave us just a remainder which is bounded in H1, because it's obtained by integral methods. Okay? The fact is that we would like to apply a fixed point theorem to the remainders mapping. So we would like to take the same phi here as the psi here. But the point is that it has to be fixed pointed into the set of functions which have C0 bounds, okay? And of course for the same value epsilon k. But it's not even obvious actually that the new remainder psi satisfies this estimate here, because it was obtained from an H1 procedure. So it comes with integral bounds, energy bounds, not with pointwise bounds. Okay? So to make this method work, what we have to do right now is to turn these H1 bounds into pointwise bounds. Okay? This is our part of the analysis. You have a function which is merely bounded in H1, and you have to show that it actually satisfies pointwise bound in this sense here. Okay. So beware, I told you that for critical equations like this one, when you get just an energy bound, you do not recover pointwise bound. That's the case of the standard bubble here. And of course this is true, but the point is here is that I'm not working with the leading term, I'm working with a remainder, right? So in some sense, so the remainder is small with respect to the bubble, so in some sense, the equation satisfied for the remainder is not a critical equation anymore. You're taking the linearization of this, so you're gaining a power in U, and you're losing the criticality here. So this process of once you have an energy bound, you get pointwise bound is wrong for the standard bubble, but it's true here for the remainders because in some sense you got rid of the bubble already. You know, the bubble is the first term in your solution, and you're looking here at the next order term, and then you can improve the estimates on it. Okay? So to do this, you have to understand how sequence of solutions blow up. So you take an abstract sequence of solution of your system. You start with energy bounds and you try to understand where it accumulates. You play with green functions. You obtain scaling invariant estimates, and you manage to improve the estimates. in 2 second-order estimates. Okay?
Wouldn't happen that the remainder develop some bubbles somewhere else?
No, it can't. So it could, but you show in the process that it can't, because the point is that in this construction step here, you know that the solution size you get is small in H1. So you know that at least its H1 norm goes to 0, right? So it cannot develop any bubble because every bubble brings the same fixed quantum of energy. Okay? But of course, it's very easy, but you have to take care of this into the process. So that's the idea of this H1 construction, actually, is that the remainder that you construct is very small in H1. And actually, you have a control on its H1 norm depending on the accuracy of the choice of this approximate solution. So that's the idea. Okay, and of course, in this epsilon k here, for now, it was just an abstract sequence, but now you will have to choose it wisely, because the epsilon k has to be the same for both the remainders. And actually, this epsilon k will depend on the structure of the system, on the precision of the ball you chose, and so on. So during the course of this procedure, you also get an estimate on epsilon k, which makes everything work. Okay? So once you do this, you're able to apply some kind of fixed point theorem and to get the same mapping. Okay? So you're almost finished your ping pong method here. You started with a solution here, you plugged it in the first equation, you went back to this one, but there are still these kernel elements here, right? So at the end of the step 2, you have a solution of the system which is almost the solution you want if it weren't for these red terms here. So you know that you have a solution of almost the system, which looks like a bubble plus a weak limit plus a remainder. You also know that the remainder is now small in a pointwise global sense. Right? And to conclude, if you were able to find a value of the parameters which annihilate these coefficients here, you would be done. Okay, you would be happy. But now you can do it because everything is explicit by now. So these coefficients here can be explicitly computed. You can just take the scalar product of this equation here with this kernel element here, which you happen to know, and then compute everything, because now you have explicit expression on all the data of your problem. So that's what you do. And to conclude the step, you use the asymptotic information on your functions to obtain an asymptotic expansion of these functions. Okay, so up to some constant, up to dividing by some constant, these functions here, they converge, so uniformly continuously, to some limiting functions. Okay? And so you're left to annihilate, in the end, some number of functions from Rn plus 1 to Rn plus 1. Okay? The miracle here of the method is that you have the same number of unknowns here, of coefficients, as the number of parameters. Okay? This is what makes everything work, because in the end, you're left with a function from Rn plus 1 to Rn plus 1, and you can choose your favorite fixed point theorem to find that it's got a 0. Okay? So this is the miracle of the method, and this is due to the fact that actually the dimension of the kernel of your approximate solution is exactly n plus 1. Okay, so this is a property of these standard bubbles, which is again related to the model equation they satisfy, and is actually related to the fact that they are descaling invariant solutions which are compatible with the scaling of this equation. So there's a slight miracle here, which is this one, which makes the method work, but in the end it works. Right? And you can compute your solution. So
can I just check I've understood? There's like an n plus 1 dimensional freedom in the bubbles.
Yeah.
You've got this capital lambda and this psi.
Yeah, and it happens that
it happens that the linearization of this scalar equation, although it's index 0, its kernel has
n plus 1
dimension n
components.
plus 1.
And it's the very important thing is that actually these kernel components are exactly the derivatives of the standard bubbles with respect to each one of the parameters. So you see your standard bubble depends on the choice of its height here. So yeah, I'm going to write it again. Your standard bubble depends on the choice of its height. So B is like lambda over lambda squared plus x minus c squared. So there's a power. So lambda is the 8th parameter, the scaling one. Psi is the center. If you take this family of functions and you differentiate it with respect to lambda and of each coordinate of psi, you exactly obtain the elements of the kernel. Right? So this is related to the fact the differentiation with respect to lambda is easy to see because it's just the scaling which makes the model equation invariant. So this is, in some sense, even though your approximate solution is degenerate, it's not, because well, the kernel of its linearization exactly consists on the derivatives with respect to the parameters you chose for the method. So that's what makes this is what makes that you have exactly the same number of parameters as the number of functions to annihilate, and in the end it works. So it's not, there's no general theorem that you apply here. You have to compute the limiting expression of these functions here and to be able to annihilate them. Right? But if you had, for instance, to any functions, it would be much harder because there would be it would be underdetermined, and so it wouldn't work. That's the idea. So I'm almost done here. Maybe the last thing I would like to do, I didn't really pay credit to the people which worked in the field. So let me, it was hard to mention the work during the presentation. So let me tell you that so these famous H1 machinery, which I've mentioned several times, which allows you to construct blowing up solutions for single equations, has been developed by some number of people. So the biggest names are probably Yun-Cheng-Wei, Olivier Rey, Manuel Del Pino, Frank Paccard, and Simon Brandle also. And so this was step one of my proof. And what I mentioned 2 slides ago, when we had to switch from the H1 estimates to the continuous estimates, uses techniques which have been developed in the analysis of critical elliptic equation in the last 15 years, and which revolved somehow around the investigation of the compactness conjecture for the Yamabe equation. Okay, so it started with an H1 theory in the 80s by Struve, and then lots of people, among which Lizou, Drouet, Marquez, Zhang, Simon Brandle again, Khoury, investigated the compactness of the Yamabe problem, and in a parallel way, by some people like Hébert-Robert, Vetois, and Tizy, the same techniques were applied to and developed to understand the general blow-up behavior of critical elliptic systems. Okay, so I needed to quote them, and I think that's all that I wanted to say. So thank you for your attention.
Any questions or comments for the speaker? I have a kind of naive question. So suppose you take a sequence of initial data sets that solve your constraint equations but blow up.
Yeah.
Each of these guys then gives you a solution to Einstein's equations on a Lorentzian manifold.
Yeah.
What happens to those? Do they blow up?
So, oh, you mean the Lorentzian manifold that you get?
Yeah. So for each k, you get a Lorentzian manifold. As k tends to infinity, the initial data is developing some sort of singularity.
So,
do you have any idea what sort of singularity happens in the Lorentzian space?
Well, no, not really. This is hard to say. So, first of all, because even so this kind of stability in large time of your Lorentzian manifold is a very complicated question. People are investigated, and it's not known. It's known only for the case of the Minkowski spacetime, And even if you didn't take, if you just took initial data sets, a sequence of initial data sets which converge, for instance, it wouldn't even be clear that their associated Lorentzian manifold do not develop singularities and so on. So that's the global stability problem, and the only thing which is known is that if you start with the R3, with the Euclidean metric, so for the Minkowski spacetime, well, up to very small perturbations in asymptotically Euclidean sense, the spacetimes which are constructed stay close to the Minkowski spacetime in a certain sense. But this is also, like, the notion of staying close is not so clear. It means that the associated spacetimes that you get have geodesics which are defined for every time, plus you have decay of the curvature along these geodesics, but that's so if you take blowing up sequences of initial data sets, you don't really know what to do. Because there is another phenomenon which could arise, is that just on a fixed manifold, taking different initial data sets might also just reduce to changing, the base manifold that you take on your Lorentzian spacetime. So when you have a spacetime manifold, which is called the Cauchy surface, generally speaking, well, you could choose any other, well, not any other, but you could choose other Cauchy surfaces, and they will all be homeomorphic. So actually, in some situations, taking blowing up initial data sets on this on a fixed surface exactly amounts to changing your surface, and so you might get the same spacetime in the end, even though you have blowing up initial data sets. So unfortunately, this is something which is quite hard to understand.
Now you couple the Einstein equation to one field. I don't have your result completely in mind, but for example, if you were to remove the field
Yeah.
Or if you would add other fields, would you then have a similar result?
So if you add like other fields at the beginning.
Yeah, so if you now describe the situation with one
Of course.
less particle, so if you had several thin particles interacting and all these things,
Well,
would you can have the same result or?
So so if you added all the different things, so you would basically get a different system here, right? So either different coefficients or maybe additional terms, and actually it will work. So it's really here. The situation will work provided you have. So there was at some point this abstract inequality. This inequality here. So this inequality here is really makes sense in its own way for coefficients which are abstract, which do not depend on the choice of the physics data. So as long as the other fields that you add still are reasonable in this sense here, you will have the same kind of results. And also if you work, for instance, with Maxwell field, if you put an electromagnetic field, what happens is that usually there is an additional term which is added here. So there is something else with another power of u, we call it up, and it might also work. So it will depend on the power of p and so on. But yeah, there is it's not, the result does not rely on the explicit form of these of the coefficients.
If this field vanishes,
so if the field vanishes totally, this doesn't work because you need, so there's this negative nonlinearity here is a problem because you need to avoid non-degeneracy. So you need somehow to assume that what is on top of it is not zero. So in particular here I assumed that this coefficient pi here is non-zero, at least somewhere. You know, it can just need to be non-zero on the whole manifold.
but if sigma is non-zero, you could.
So if sigma is non-zero, if sigma is non-zero, it's not. So I would say it's not obvious that if sigma is only non-zero, the same thing will work. I don't. Yeah, I think it should be true, but I wouldn't. Well, I wouldn't say it's obvious. So I never. I didn't really try to prove it, but it might be. Well, I would say it's true, but still there might be some compensation phenomena here inside. So you wouldn't. It would have. It might be true, but it's not trivial at least. So you know.
If there are no more questions, then let's thank Bruno again.